our speaker. So I'm delighted that our speaker for this year's Simon's lecture is Bhargav Bhatt. Bhargav Bhatt, from the University of Michigan. He received his PhD from Princeton under the direction of Johann de Jong in 2010. He was a postdoc at Michigan, and then after a couple years at the Institute, he went back to Michigan as a regular faculty member, where he's now the Frederick and Lois Gehring Professor. Bhargav has won many honors. I'll just mention he was a Packard Fellow. He was last year named a Simons Investigator, and he won the New Horizons Prize in the last round of these awards. So he's going to speak on, give 3 lectures on p-adic algebraic geometry, and today the first one is an overview. And let's see, Bhargav, you need to, I'm not seeing.
Yeah, let me share my screen.
Yeah, we have to. So thank you very much for coming, and I'll turn the floor over to Bhargav.
Great, thank you. Can you see my screen? Okay, great. Sorry, I just need to adjust the visual settings here.
Is there a way to make it a tiny bit bigger, or is that complicated? Never mind.
So there is this presentation mode option where it makes it bigger, but then less information is visible on the screen at any given moment. And
I take it back.
Okay, let's try with this, and if it doesn't work, I'm happy to play around with it. Okay, great. Thanks a lot. Thanks, Rob, for the introduction, and also for this very generous invitation. I'm very honored to be speaking here, albeit virtually. I have a lot of friends in Stony Brook, and I hope I get to see them before long in person. Okay, great. So the title of my lecture series is p-adic algebraic geometry. And so as I wrote in the abstract, what I want to convey in this series is some sense of the many advances that have taken place in the subject over the last 10 years. A number of these advances have been kind of on the foundational side. And then there are sort of further downstream applications in rather different areas of math. And it might be hard as an outsider, at least, to see sort of what links something in homotopy theory to something in commutative algebra. And one of the things I want to do in this lecture series is give you a sense of what these sort of connections are that allow us to sort of move information between fields. And so in the talk today, I just want to give an overview. So I will tell you a little bit about background on what the p-adic numbers are, why we care about them, a tiny word on what these advances are, without really going into any detail, and then maybe mention some applications. And then in the follow-up talks, I will go into more depth in 2 of those applications where we'll see sort of more about what the advances are. So that's the plan. And it's a Zoom talk, but please feel very free to ask questions, because it's much easier for me to be giving the talk if there's more interaction. Okay, great. So for the rest of the lecture series, let me fix a prime number p. It can be any prime number. At some point, I will make some assumptions on the prime, and they'll be towards the end. Okay, so since it's a talk on p-adic algebraic geometry, let me first remind people what the p-adic numbers are. So what are the p-adic numbers? Okay, so there's multiple perspectives on the p-adic numbers, and I just want to recall a couple of them because I will use them to motivate what comes later as well. So this sort of first definition one might have seen of the field of p-adic numbers. So it's maybe first thing I should say is that it's a field. And the first definition one might have seen of this field is something analogous to the real numbers. So if you remind yourselves in sort of baby analysis, the way real numbers are defined, what does one do? You take the field of rational numbers, and then you concoct a metric on it, the sort of standard notion of size. And then you observe that, well, okay, this field is not quite complete for this metric, so I have to complete it. And this completion process gives me the real numbers. And so in this procedure, there's a parameter, which is the metric. And you might wonder what happens if there are other metrics and you do the same. And that's where the p-adic numbers come in. So there's a classification theorem of Ostrowski that basically all the metrics that are allowed that you can have on the rational numbers are either the standard metric or the p-adic metric, one for each prime number p. And so let me just quickly remind you what this is. So there's a p-adic metric on Q. So there's just a natural p-adic metric on Q. And what it does is that it measures the number of times a prime number p divides the rational number. So if it's an integer, that's literally what it means. If p shows up to high power in the prime factorization of the number, then it's p-adically small. And if it's a rational number, you write it as a ratio of two things, pull out all the factors of p, and then do the same thing. And so here's a formal definition of what this could mean. So given a rational number a over b, its p-adic norm is defined to be 1 over p is some small number, and then I raise it to a power, which is the difference of the p-adic valuations. Okay, so that's just the definition. If you sort of think about what this means, but the sort of most important feature is that the powers of p go to 0. And so this is a metric, and then if you complete Q with respect to this metric, you get QP, which is the field of p-adic numbers. And so if you want to write down what elements of this field look like, you can write them as power series, where the coefficients are rational numbers, and the variable now is the prime number p itself. Somehow, because powers of p are going to 0, you're allowed to write such expressions down, and they give you all the p-adic numbers. And so this is more or less by construction, this is a complete valued field, meaning it's complete for its topology, and this topology is defined by a norm. The same formula gives you a norm in the p-adics as well. Okay, so that's what the p-adic numbers are. Maybe the first point of departure in which the theory starts differing from the theory of real numbers is that this metric is actually an ultrametric. So it's a non-Archimedean metric. So here's kind of the observation, which is this is an ultrametric, which means it satisfies the strong form of the triangle inequality, which makes life a lot easier. So the absolute value of a plus b is bounded above by the max of the absolute values of a and b. Right, it's not just the triangle inequality, it's better than that. And so one consequence of this is that, you can sort of contemplate the set of p-adic numbers whose absolute value is less than 1. So let's say a set of all a and qp, the absolute value is less than 1. And if you did this over the real numbers, you just get the unit interval between the interval between -1 and 1. This is just some topological space. It doesn't have any additional structure. Like if you take two numbers and you add them together, even if the numbers were individually smaller than 1, the sum could be bigger than 1. But that doesn't happen over here because of the triangle, the strong triangle inequality. And so what you get is that this is actually a ring. Okay, and so this QP, QP is a field. ZP is a ring, it's not a field. And it's easy to see why it's not a field. If you think about what the prime number P itself, certainly the absolute value of P is smaller than 1 because P is small in this metric. So P lives inside ZP, but its inverse does not, because its inverse is absolute value, the inverse of the absolute value of P. So it's bigger than 1. And so this is a ring, but it's not a field. And in fact, this is a ring that sort of glues together characteristic 0 and characteristic P. And so I'll come back to that statement in a second. I wanted to give one more sort of perspective on the p-adic numbers before I talk about the relation between the characteristics. And so, right, this was the analytic perspective on the p-adic numbers through the metrics. There's also an algebraic perspective, which will be very useful later. So let me mention that. And so the algebraic perspective, from the algebraic perspective, it's more natural to define ZP first and then QP rather than the other way around. And so algebraically, what happens is that ZP, this is a ring, and this ring has a very kind of easy description. There's just a formula in terms of Z. And so the formula looks a bit complicated, but I'll sort of unwind it. So it's an inverse limit of Z mod P to the NZ as n goes to infinity. And so what does this actually mean? This means that its elements are sequences an, n bigger than 1, say, where an is in z mod p to the n, and they satisfy the congruence that an plus 1 is congruent to an mod p to the nz. So it's a set of all compatible sequences like so. And it's not so hard to convince yourself that if you have a sequence like this, if you just naively pick representatives of each of the sequence in Z, so pick a lift an tilde of an in Z, then the sort of sequence you get this way in Z will be a Cauchy sequence for the p-adic metric. Precisely because of this equality over here. It tells you that the difference between the lift of an plus 1 and the lift of an is divisible by a big power of p, and therefore it's small in the p-adic metric. And so this is the algebraic perspective on ZP, and then QP from this perspective is obtained by inverting P. Maybe it's easier to see the fact that QP is ZP with P inverted from this discussion over here. If I have an element of QP and I scale it by a huge enough power of P, its norm is going to be smaller than 1. And so therefore it's going to be an element of ZP. Okay, and so what's the picture? The picture is the following. So you have ZP. You can invert P to obtain QP. And you can also kill P. And what you obtain this way is just Z mod P, which I'll write as FP. Okay, so maybe I don't spell out why this is true. It's an easy exercise to see that ZP mod P is FP. Just from this definition. But the sort of important takeaway for us is that this ring over here is a ring of what is called the mixed characteristic ring. It doesn't contain a field, but it has sort of a natural and interesting maps to two fields. This field QP of characteristic 0 and the field FP of characteristic P. And this is one way in which it often shows up. It shows up when you try to relate some geometric information in characteristic 0 with some geometric information in characteristic P. ZP is sort of the glue that binds them together. Okay, are there any questions so far? Okay, and so let me mention also a variant of this, which is more relevant maybe for my lecture series, I mean, I'm an algebraic geometer, and as an algebraic geometer, it's much easier to be doing algebraic geometry over an algebraically closed field. You want to sort of ignore number theory complications, at least at the first pass when you're trying to understand something. And the field QP is not algebraically closed. Its Galois group is in fact quite massive. And so we want to pass to the algebraic closure. And so that field has a name, and so I'll call that, it's called CP usually. So it's QP bar. It's the analog of replacing R with C, the real numbers with the complex numbers. But there's a subtlety, which is the complex numbers have degree 2 over the real numbers. So they're a 2-dimensional vector space. In particular, they're complete for the natural topology, because R is complete and a finite dimensional vector space over a complete field is complete. But this is, QP bar actually has infinite degree over QP because the Galois group is enormous. And so this is not complete, and you have to complete it. And then there's a small miracle happens, which is that the completion is also algebraically closed. So you don't have to worry about this process of iterating this operation many times. And so I will refer to these as the p-adic complex numbers. And this is sort of going to be the ground field that we care about. And just like QP had this interesting subring ZP inside of it, same formula gives you an interesting subring over here, which is OCP, which is the set of all p-adic complex numbers whose absolute value is less than 1. And there's a similar picture. So I explained the picture over here, how ZP relates fields of characteristic 0 and characteristic P by more or less the same reasoning. So does OCP. So here's OCP. Again, inverting P gives you CP for the same reason as before, because you can scale an element by a big enough power of P to make its norm smaller than 1. And if you kill P and slightly more, now you don't get FP, rather you get FP bar, because you already enlarged CP sufficiently to join solutions of all monic equations. And so you can also reduce those solutions mod p, and you get the algebraic closure of FP bar.
So FP bar is the algebraic closure of FP.
Right, yeah, thank you. FP bar is the algebraic closure of FP. And so this is kind of, from a geometric perspective, this is a more natural object to use if you want to relate characteristic 0 and characteristic p, because it's relating an algebraically closed field of characteristic 0 with an algebraically closed field of characteristic p, rather than something arithmetically interesting here with something arithmetically interesting here. And so this is kind of going to be one of the key players of this of these talks. And I want to sort of highlight a tension here already that's visible, which is if you're a trained algebraic geometer, you like your finiteness conditions. Noetherianness is kind of the lifeblood of algebraic geometry, and it's a finiteness condition that we sort of are just, I don't know, at least I was trained to just internalize, and sort of everything was Noetherian. And the string OCP is not Noetherian. You can sort of easily check that you can, since you can extract all roots of P, you get lots of ideals which are not finitely generated. And so in p-adic analytic geometry, there's invariably some tension between wanting to work over algebraically closed fields and wanting to work with Noetherian rings. And one of the sort of lessons of the last 10 years, I think, has been to embrace the former and forget about Noetherianness, because we often end up getting better results this way. Okay, and so maybe I should make a couple of remarks on these definitions. So maybe the first remark is that if you're uncomfortable with the objects I've just introduced, maybe it's worthwhile to remark that CP is isomorphic to the usual complex numbers, just as a field. So this uses the axiom of choice, and I understand if you don't want to buy it, but any two uncountable algebraically closed fields of the same characteristic and the same cardinality are isomorphic. And so therefore CP is isomorphic to C. But at least at first pass, this is kind of useful because it allows you to pretend that you kind of know how life works over here. I mean, after all, it's the complex numbers. It's something a lot of us use every day. The second comment I wanted to make, which is something I already said verbally, but let me write down, is that the Galois group, GQP, by which I mean the Galois group of CP over QP, by which I mean the automorphisms of CP, or maybe I should say continuous automorphisms of CP over QP, is enormous. So this is one way in which it is different from enormous. It is different from what happens in the classical setting of the real numbers and the complex numbers. And this largeness of the Galois group is actually quite useful. So first of all, if you're a number theorist, this is one of the fundamental objects of study in modern algebraic number theory. It's a part of the absolute Galois group of Q, and sort of one can somehow more or less convincingly argue that a large part of modern algebraic number theory is dedicated to studying absolute Galois groups like this.
Bhargav,
yep.
There's also the Galois group of QP over QP bar. What's the relation?
They're the same. So any continuous automorphism of CP, giving a continuous automorphism, any automorphism of QP bar over QP extent is continuous and extends uniquely to a continuous automorphism of CP.
Thanks.
Thanks. Right, so this largeness actually has a very practical consequence, which is maybe I'll come back to in my third talk. So it's one way in which p-adic Hodge theory ends up being slightly stronger than classical Hodge theory. Because in p-adic Hodge theory, the group that ends up acting on things is this uncountable algebraic group, GQP, rather than complex conjugation, Z mod 2. And because of this, we sort of get more decompositions in p-adic Hodge theory than you might naively expect from classical Hodge theory. So I'll come back to this at the end. But okay, that was my mini introduction to what the p-adic numbers are. Are there any questions?
Thank you.
Oh, okay. So that was Dennis, right? I once gave a talk in this seminar. It was my very first time, and it was about p-adic comparison theorems. And first, I was not prepared for a discussion of the p-adic numbers at the time, and so that kind of that's maybe one reason why I decided to talk about the p-adic numbers at length today. Okay, so this is what the p-adic numbers are. Let me now try to address the question of why one might care about them. So how do these come up? So if you're a practicing mathematician, maybe you don't actually care about the p-adic numbers for their own sake, but you might still be interested in knowing how they might arise naturally in some constructions you're doing. And so I wanted to, I mean, there's no unique answer to this question. There's tons of answers. I'm just going to highlight two answers that are sort of relevant for my talks. So I want to first mention the extrinsic perspective. So they arise extrinsically, meaning they arise. So maybe it's best to just go back to my definition of ZP up here. So I gave this algebraic definition of ZP. It was the inverse limit of Z mod P to the NZ as n goes to infinity. And obviously in this definition, the fact that I use Z was not important. I could replace Z with any abelian group, for example, and the same procedure would make sense and it would produce a new abelian group. And so that's called the p-adic completion of an abelian group. And that's one way in which the p-adic numbers often arise. So as p-adic completions, or maybe I should say as completions for the p-adic topology. Of abelian groups. By which I mean that if you take an abelian group and you p-adically complete it, what you get is a module over the p-adic numbers. And so that's the sense in which the p-adic numbers are arising. But in fact, if you're sort of sufficiently sophisticated, there's no reason to sort of stop at abelian groups. You can do it with fancier objects. And one of these will come up in my lectures. And so I just wanted to mention it. So example. And so this goes back to Dennis Sullivan's early work, which is that it's possible to p-adically complete a space, not just a set, or not just an abelian group. So if X is a topological space, then there exists a natural p-adic completion X hat of X. And I don't want to give the definition, but maybe I'll just point out sort of what happens in good cases. So such that the homotopy groups of the p-adic completion are the homotopy groups of X p-adically completed in nice situations. And so it's some operation at the level of spaces that incarnates the p-adic completion operation at the level of homotopy groups. And this allows you to sort of decompose a topological space, especially from the perspective of homotopy theory, into sort of its p-adic pieces, one for each prime p, together with something rational. Okay. And so this is going to be kind of a primary source of examples for us, p-adic completions of objects that a priori are defined without reference to p. But there's also sort of some intrinsic reason to care about the p-adics. So intrinsically, one reason to care about them is, so over the complex numbers, the theory of complex analytic spaces is this kind of extremely rich theory that you have a notion of analytic functions. You can glue spaces together along nice holomorphic maps to produce complex analytic spaces. There's complex Hodge theory, and so on. And so there's a completely parallel story in the p-adic setting. So there exists a good theory, a good notion of p-adic analytic functions. And this leads sort of naturally, well, I say naturally, but it took like 30 years and many failed attempts, naturally to a theory of p-adic analytic spaces, p-adic Hodge theory, etc. And so let me give, I don't want to obviously spell out what these things mean, but I'll give an example. So this example is due to Tate, and it's in fact the example that motivated the theory of p-adic analytic spaces in the first place. So what he observed is was a p-adic analog of complex uniformization. So if you're working over the complex numbers, it's very fruitful to think of elliptic curves as quotients of the complex numbers by a lattice. So C mod lambda gives you an elliptic curve, and this perspective of thinking of the elliptic curve, which is something an algebraic geometer might care about in terms of this uniformization by C, is helpful in proving things about it. Now there's a slight twist of this where if you write your lattice as z plus z tau, instead of saying c mod lattice, you can say c star mod e to the 2 pi I tau. You first quotient out by the z coming from the first factor, and then you quotient out by what's left. And it's the second description as a quotient of C star that has a beautiful p-adic analog. So Tate proved the following. So for any p-adic complex number whose absolute value, well, I should say non-zero. So maybe with 0 less than the absolute value of q less than 1, the space, which I will call EQ, is you take the p-adic complex numbers, you remove 0. So CP star, if you like. Oops. And then you mod out by q to the z. So the scaling action of q. So what he proved is that the space is naturally an elliptic curve. Meaning it's an algebraic curve over CP. But to write down this algebraic parameterization of EQ, you need to use analytic functions on this space. And so this theory of p-adic analytic spaces allows you to make sense of quotients like this. And the final quotient is something you care about in algebraic geometry, is just an elliptic curve. But to realize it in this form, you need to use this theory of analytic spaces. And this is actually incredibly useful because having a presentation like this makes it very easy to compute things. So over the complex numbers, one reason having uniformization is useful is that the lattice that you're quotienting out by gives you the fundamental group of the elliptic curve. There's a sort of parallel story over here where the first homology of this elliptic curve is completely described in terms of basically this element Q. And now there's the additional advantage that that the Galois group that I was talking about earlier acts on everything. So if your element Q was actually invariant under the Galois group, then the quotient is defined over QP, and so the Galois group acts on everything, and therefore it acts on the homology, and it gives you an example of what is called a Galois representation. And we care a lot about understanding these Galois representations in number theory, and having this explicit presentation makes it very easy to compute with them. Okay, right, so these are maybe two examples of how p-adic numbers arise naturally and are useful. I want to sort of switch gears now and talk a little bit about what's been going on in the last 10 years. And so maybe I should just pause again and ask if there are any questions before I do that.
Well, maybe one question. In the cohomology of the elliptic curve, since you have this action, I mean, do the eigenvalues play a role?
The eigenvalues play a role. Well, I mean, I can just tell you what the answer is. So usually you do this cohomology with finite coefficients. And so ultimately what you're trying to understand is what the torsion, sorry, I shouldn't use black, what the torsion points on this curve look like. And this is a description, which is a quotient as a group action. So the torsion points are going to look like either torsion points here or roots of Q. And so that gives you a very explicit description of what the cohomology is. It's an extension of two objects, each of which you understand concretely.
But I was thinking more about the fact that if you take an element of the Galois group, then it gives an automorphism in cohomology, and that has eigenvalues. If you look at this picture of a finite field, that gives you the weights of a. So is there a picture like this here, or?
Right, that's what I was trying to describe. I was trying to describe the action of the Galois group on the homology by describing the homology explicitly. So I was thinking of homology in terms of the torsion points. And once you do that, the torsion points are given by roots of unity, which are the things coming from here, and roots of Q. And Galois just acts on them as it normally does. It's the standard action on roots of unity and the usual scaling by roots of unity action on Q.
Oh, okay, thank you.
Okay, so that's how the p-adic numbers arise. And so I started off the talk by saying that there have been a bunch of new advances on the foundational side that have really moved the subject forward. So what are some of these new techniques? Oops. So there's a few related foundational advances, and I'm not going to talk about all of them, but I'm going to highlight two of them, which are sort of important for my talks and also somehow are easier to understand at first pass. So the first one is certainly the theory of perfectoid spaces. And so this is, the theory was due to Scholze in his PhD thesis, and also more or less simultaneously by Kedlaya and Liu. And it sort of builds on a lot of prior work in the subject. Most of all, Faltings' work on p-adic Hoche theory in the 80s. And so I cannot give you a definition of perfectoid spaces in this talk. That would take up the whole talk and not be a general audience suitable talk. But I can give you a slogan definition. So these spaces are rough. I'll give you examples. So these are infinite sheeted covers of analytic spaces, so p-adic analytic spaces. With some very special properties. And so the special property are that, it's the following. So that are infinitely ramified in characteristic P. Okay, so there are nested scare quotes in this sentence. So please take it with many grains of salt. And so infinitely ramified in characteristic P roughly means that in the equations that you need to sort of describe these spaces, all the elements have lots of P power roots. And so instead of sort of spelling this out, I think it's easier to just think of examples. So let me give you two examples, which I think make sort of clear what's going on. So the first example is the perfectoid unit disk. And so let me first recall what the standard closed unit disk is. It's just what you think it is. So it's the set of all p-adic complex numbers whose absolute value is less than 1. This is what I called OCP earlier, but I was thinking of it as a ring at the time, and now I want to think of it as an analytic space. So it's a small disk. Now if the absolute value is less than 1, I can sort of look at the p power map on this space. If z has absolute value less than 1, so does z to the p. And so what you get is a tower that looks like this. The maps are all z goes to z to the p. And so the inverse limit of this space is an example of a perfectoid space. So I think in sort of standard topology, if you do an analogous construction with a circle, I think it's often called a solenoid or a p-adic solenoid. And this is kind of the p-adic analytic version of that. Well, it's with the disk, but it's the same idea. And
so
the second,
on the boundary of the disk, you would get the analog of the p-adic solenoid.
Right. Yeah. And you can do more or less the same construction with other objects which have other spaces which have these endomorphisms that have something to do with P. So another such example is multiplication by P on a torus. So take E to be an elliptic curve, like the one I wrote down earlier, for example. Oops. Or CP. And then the statement is that, again, the inverse limit of multiplication by P on this curve is perfectoid. Actually, I forgot to look up the reference of this. So proving something is a perfectoid space is slightly non-trivial in some situations. And I think for elliptic curves, it can be non-trivial. So there's a paper that came out of the Arizona Winter School a couple of years ago that proves the statement. So I should have looked it up earlier. I'm sorry.
So on the inverse limit, raising multiplication by P becomes an isomorphism by bijection.
Right.
We use this in dynamics to create that bijection.
Right. It's sort of it's the universal way of making the map a bijection by sort of passing to the left.
Yeah.
Right. So what I wanted to mention about these two examples is, if you're sort of, again, if you're trained from kind of a more standard or classical algebraic geometry perspective, these spaces look huge. You've sort of lost all finiteness conditions. But it's nevertheless surprising that there is actually a good handle on what these objects look like. And in fact, in some ways, it's actually better than what happens in usual in finite type situations. So let me just say it this way. So surprisingly, perfectoid spaces are actually sometimes easier to understand. So maybe I'll just say are simpler in some ways than usual analytic spaces.
Bhargav, can I ask a question?
Yes, yes, please.
So the two examples have a little bit different flavor, right? Because the first one is ramified, even if you don't put the word characteristic P, and the second one is not. So what's the
second one is ramified.
But no,
so it's ramified in characteristic P.
No, but not in characteristic 0.
Right.
But the other one is ramified in characteristic 0 and characteristic P. So they're both, what doesn't, can you say something about the difference between the two?
So I think the fact that the first one is ramified in characteristic 0 is kind of a red herring. Like I could replace D with the, as Dennis was saying, I can replace it with the boundary of the disk, with the circle, and the same example would still be valid. And then your objection would go away because it would be unramified in characteristic 0. The important feature is that it's this thing. It's the thing that makes them perfectoid is the fact that it is ramified in characteristic P. There's no conditions on what happens in characteristic 0.
Okay, so I understand in the second case what it means to be ramified. You take the curve, maybe you reduce it modulo P, and then it's ramified. But in the first example, what does it mean?
So there's a similar story. Like you can talk about an integral model of this disk, and then it just means the same thing.
Thank you.
Does it work if you perturb, if you do look at Z squared plus C, and C has norm smaller than 1? Does it become perfectoid too?
I believe that is true, but I would need to. I'm like 80% sure right now it's true, but I would need to check more carefully to say anything more than that. Because somehow, yeah, I think it should be true. Right, so surprisingly, I was saying perfectoid spaces are simpler than usual analytic spaces. And one reason for this is that, so Schulze proved this kind of remarkable theorem called the tilting equivalence that says that perfectoid spaces can be completely understood in terms of objects that live in characteristic P. And there's some like precise statement about like an equivalence of categories. But so what this means is that you can pretend that these inverse limit objects are actually living in characteristic P. And then you might wonder, okay, why is this actually a good thing? Like, how is this actually making my life easier? One way it makes your life easier is that there is this canonical endomorphism, the Frobenius, that acts on everything that lives in characteristic P. And so now you get some additional structures at this kind of infinite level object that you were not able to see at the finite levels. And there are sort of precise theorems that say that perfectoid spaces are simpler, for example, in terms of their cohomological dimension and so on. Great. So that was one foundational advance. And then the second one is this theory of prismatic homology, which I will sort of talk more about in the second talk. It's related. So this is some joint work of myself and Schulze, building on some previous work we did with Matthew Morrow. And mostly I'll talk about this in the next talk. For now, let me just say that this is an integral cohomology theory. So
it's a what?
Integral cohomology theory.
Oh, integral.
It has ZP coefficients. So it's an integral cohomology theory that unifies, or maybe I should say for what? So integral cohomology theory for smooth, projective, so the nicest possible geometric objects, X over ZP, unifying the previously known ones. So in this context where you have a geometric object that lives over the p-adic integers like ZP, So just think of like you have a bunch of equations with ZP coefficients, and then they satisfy some conditions. So you can take those equations and either regard them as equations over QP by inverting P, or you can go mod P and regard them as equations over FP. So you get these two algebraic varieties, one living in Kiersich 0 and one living in Kiersich P. Each of these varieties has its own preferred cohomology theory. So the words that get thrown around usually are like étale or de Rham or crystalline or de Rham width and so on. So there's a whole kind of zoo of p-adic cohomology theories associated to this situation. And what prismatic homology roughly does is that it sort of puts most of them, at least, together in one framework. So there's a single cohomology theory which lives over a 2-parameter base. And then if you restrict to various loci in this 2-parameter situation, you recover the existing cohomology theories. And this gives kind of more new relations between these cohomology theories that we did not know about before. But as I said, sort of most of this will come in the second talk. All previously known cohomology theories. Is that okay? All right, so what I want to do in the remaining time today is switch today and talk about these applications that I promised. And so these foundational advances, I mean, okay, great. They sound nice at some conceptual level, but I want to sort of convince you that they're actually useful in proving theorems, concrete theorems. And so let me talk about the applications now. And I will try to bring the discussion back to which foundational advance gets used where, but of necessity, it's going to be slightly vague. So maybe the first one I want to talk about is a number theory. And so this is I think it's fair to say that this is one of the early kind of slam dunk applications of the perfectoid theory. So this was Scholz's torsion Langlands correspondence. It was 2013. And what he basically does in this paper is he sort of expands the scope of the Langlands correspondence to allow objects with coefficients in Kiersich P rather than just Kiersich 0. So let me just write down a vague statement and then I'll talk about why this is important. So for many number fields, any mod P automorphic form on GLN over the number field has an attached Galois representation. So the representation goes from the absolute Galois group of the number field to GLN over FP, or really FP bar. Okay, so this is obviously a vague statement. What I want to point out is
what's an automorphic?
Sorry?
What is an automorphic representation?
It's an automorphic form on GLNF, right? Oh. So what I mean over here is, so associated to any reductive group over a number field like GLNF, there is this locally symmetric space. So for GL2 over Q, you would get the modular curve. Otherwise, it's more complicated. And a mod P automorphic form just refers to certain cohomology classes on this locally symmetric space. And so what his theorem is really saying is that associated to cohomology classes on the locally symmetric space for GLNF, we can construct interesting Galois representations, and they're sort of related in some precise way predicted by the Langlands correspondence. Now, traditionally, the Langlands correspondence was only formulated with coefficients in something in a Kiersich 0 field. So cohomology classes with Q coefficients rather than with FP coefficients. There are qualitative theorems by various people that say that there is a ton of torsion in the cohomology of these locally symmetric spaces. It sort of grows exponentially as some natural parameters in the situation change. And so there are many, many more mod P automorphic forms than Kiersich 0 automorphic forms. And so correspondingly, his theorem is producing many, many more Galois representations than were previously known by the Kiersich 0 theory. And this kind of greatly sort of changed the lay of the land in the Langlands correspondence. And maybe most recently, I should say that in 2018, there was this 10-author paper which uses this theorem, amongst many other results, to prove what's called the Satotate conjecture for elliptic curves over number fields. So it's some concrete statement about the distributions of the number of points on solutions of cubic equations over a number field as so solutions mod p of a cubic equation over a number field, and the proof of that uses basically everything that we know about the Langlands program. And so it's a useful theorem. This is not a lecture series about the Langlands correspondence, and I'm not an expert on this. So if you're interested in this, I heartily recommend that you read the original sources and not listen to me blabbing on about it. But I just wanted to point out the connection to what I was talking about before. So why is this theorem an example of an application of one of these p-adic techniques I was talking about? After all, the statement of the theorem has nothing p-adic in it. I mean, it was a statement about a number field which has tons of primes. And the only place where a prime shows up is when I talk about reducing mod p, but that's a purely kind of mod p phenomenon. You don't need p-adic numbers to talk about that. And so the key technical theorem that sort of underlies this theorem I've written up here is the following. So the key technical theorem is the following. So I mean, it's also Peter Schulze. And so what he says is it's the statement that a certain set is naturally a perfectoid space. So I'm going to look at AG P infinity. So this is notation. This is the set of all abelian varieties over CP with a trivialization. So maybe I call the abelian variety A with a trivialization of its first homology. With coefficients in the p-adic numbers. So the first homology with ZP coefficients. So if I replace the word ZP over here with Z, just the integers, then this would be the Siegel upper half space. It's how one sort of thinks about the space of all abelian varieties. It's you look at the Siegel upper half space and then you quotient out by some group action. And so here
what does the word trivialization mean?
An isomorphism with ZP to the 2G.
Okay.
It has to be a symplectic isomorphism. So the key technical theorem is that this is a perfectoid space, is naturally. And there's some kind of complicated argument that allows you to translate information about mod p automorphic forms on GLNF to information on a space that looks like this. And then the fact that it is perfectoid allows you to use this perfectoid machinery to construct the attached Galois representation. And so this is maybe one example of where the perfectoid theory is showing up in kind of a subtle way. It's not involved in the statements, but it's showing up in the proof strategy. So that was the first application I wanted to highlight. That was one in number theory. I also want to talk about one in algebraic geometry, which I will discuss in my, this is in my third talk. And this is rather recent, so this is actually from last year. So it concerns vanishing theorems. So in algebraic geometry, we're often interested in when certain cohomology groups attached to algebraic varieties vanish. The sort of standard example of a vanishing theorem that's incredibly useful is Kodaira vanishing. It says that if you have a negative line bundle on a compact complex manifold, then its cohomology groups in low degrees are going to be 0. And these statements are useful not necessarily in their own right. I mean, they are interesting in their own right, but they're also useful in sort of practical applications, because often what happens is that you're trying to solve some geometric problem, and the solution you want to do an inductive argument to solve the geometric problem. You solve the problem on a hypersurface, so on something of dimension 1 smaller, and you want to lift the solution from the hypersurface to the ambient space. And often what happens is that the instruction to lifting a solution from a hypersurface to the ambient space ends up living in a cohomology group in an H1. You sort of think about some exact sequences. And so knowing that some cohomology groups vanish allows you to translate this into some concrete statement about the obstruction not to solving some geometric problem not being there. And so then you can run this inductive argument to lift the solutions up. And so Kodaira vanishing is a theorem that's a purely characteristic zero theorem. The proof uses Hodge theory, and in fact, the theorem is actually false away from characteristic zero. Nevertheless, last year, I was able to show the following. So it's what happens in mixed characteristic. And I'll write down a vague statement, and then I'll write down a precise consequence in a moment. So Kodaira vanishing holds true up to passage to finite covers. In mixed characteristic, meaning in all situations. And so what this means is that there are certain spurious cohomology classes that you don't want to be there. They're there. We have examples saying that they're there. But what the theorem is saying is that you can always find some finite cover of your space where after you pull back to that finite cover, those classes are not there. So it permits solutions of these geometric problems by induction at the expense of passing to a finite cover, which is often good enough in applications. And so let me sort of, in a couple of remarks about this theorem, let me sort of give you a concrete version of what this theorem is actually saying. And then if you're bored, you can just try to prove it and tell me.
Excuse me. By finite cover, you mean a finite unbranched covering space?
No, definitely branched.
Oh, branched.
Because the theorem is interesting for simply connected spaces. So you have to allow branching.
Okay.
Do you use alterations to prove this?
Alterations are part of the proof, yeah.
Okay.
But right, so, well, maybe actually in the interest of time, I shouldn't give the concrete version of the theorem. I can do it at the end of the talk if someone wants. I will do it in the third talk. But maybe I'll just mention, so the proof of the theorem uses this prismatic machinery as well as a p-adic Riemann-Hilbert correspondence, which we develop for this purpose. Well, I shouldn't say correspondence, p-adic Riemann-Hilbert functors for FP sheaves. And so this is joint work with Jacob Lurie. And so what I mean over here is that sort of usual complex Hodge theory allows you to understand the sort of Q, like constructible sheaves, for example, with Q coefficients on a complex variety rather explicitly in terms of some geometric data. But you might wonder, like, if I have a complex variety and I have a sheaf with Z mod P coefficients, is there still some geometric way of understanding this? And that's the kind of understanding I'm hinting at over here. And maybe the second remark I wanted to make is, so this theorem sort of leads to, well, meaning, so a standard application of vanishing theorems is in birational geometry. And so it's unsurprisingly, this theorem over here we were able to use it in birational geometry to sort of prove the following. So this is joint work with a bunch of people whose names I won't write out, but I'll just say it. So Linchuan Ma, Joel Patakvali, Carl Schweid, Kevin Tucker, Joe Waldron, Jakub Witajek. And also independently was noticed by Yoshikawa and Takamatsu. And so what basically the statement is that the minimal model program holds true in dimension less than or equal to 3 in mixed characteristic. So this is, for context, the statement is sort of completely known in characteristic 0. In characteristic P, there was a work by Christopher Haken and Chen-Yang Xu that established the same statement. So in dimension less than or equal to 3, one can do the MMP. And now we're saying we can do it in mixed characteristic. I forgot to say, so when P is bigger than 5. And the strategy is somehow similar, that we have vanishing theorems, so we can sort of do some inductive lifting arguments to go from solving the problem on surfaces, which was sort of more classical, to doing it for threefolds. But then we get stuck at threefolds for various reasons. One reason being that resolution of singularities is not known beyond dimension 3. Okay, right. So this was an application in algebraic geometry, and I will sort of come back to this in the third talk, providing some more context. I was planning to say something about one more application. There are only, I believe I have like 5 minutes left. Is that accurate?
You can, we started a couple minutes late, so you can go a couple minutes over.
Well, I'll try not to go too much, but I want to at least mention this. So this is in homotopy theory. And the motivation for this is a classical result of Atiyah and Hirzebruch. So Atiyah and Hirzebruch observed that if you have a topological space X, then it's K-theory. K-theory space, K of X. So what they prove is that there's a spectral sequence which goes from the singular cohomology of X to the K-theory of X. And so sort of a slightly sloppy way of saying it is that K of X is filtered by the singular cohomology of X. What I mean precisely is that there's a spectral sequence which goes from things involving singular cohomology to things involving K-theory. So this is Atiyah Hirzebruch. Well, I guess when I say it this way, it's using Bott periodicity. And so the notion of K-theory makes sense in many different contexts. It's not just restricted to topological spaces. You can talk about the K-theory of a commutative ring, for example. Quillen did this. He defined a K-theory space attached to a commutative ring. And then you might wonder if there's a similar statement. Like, is there some easy way up to some extensions or spectral sequences to compute the K-theory of a commutative ring in terms of something simpler? And this is the theorem. So this was joint work. This is the same joint work I mentioned earlier with Morrow and Schulze. And it also relies on some work of Clausen, Matthew, Morrow. And I will say one version of the statement. There are sort of fancier statements one can make, but let me just say the simplest statement. So let's say R is a p-adically complete ring. Then one can define this K-theory of R. I can complete it for the p-adic topology in the sense that I was mentioning earlier, like a space has a p-adic completion. And so I sort of want to zoom in on all the p-adic information that's present in the algebraic K-theory. So I complete it. And there's a small decoration, which I will not explain verbally. It's a Tal K-theory. And then the statement is that this is filtered by something that I will denote by ZP of J. And so it's parallel to the Atiyah Hirzebruch spectral sequence. We're saying that there's a recipe to compute the Tal K-theory of a ring R in terms of some sort of more simpler information, or arguably more simpler information. And so in the interest of time, let me just say that what this is. So this is called Syntomic Homology. And this is defined using Prismatic Homology. And it's easier to compute than K-theory. It's not as easy as singular cohomology of a topological space, right? I mean, like this statement over here is incredibly useful because now you can just actually go to town. You want to compute the K-theory of a space, you try to understand singular cohomology, and you try to understand the differentials in the spectral sequence. If you have this, if the space is presented by a nice finite CW complex, understanding singular cohomology is no problem. And then you might hope that the extensions work themselves out in the spectral sequence. The situation here is not quite the same yet. Syntomic homology is still hard to compute, but it is definitely easier to compute than the K-theory of the space. And so I will just say that the theorem has led to a bunch of new calculations in K-theory, and in fact, Hesselholt has actually used this machinery to give a purely p-adic proof of Bott periodicity. So you can sort of reverse engineer the whole thing and reprove Bott periodicity this way. Of course, that's kind of a ridiculous thing to do, but it at least I think indicates that there's something going on. And so in my second talk, what I want to do is I want to talk a little bit about what prismatic homology is, and I'll try to explain the motivation. So one of the early constructions of prismatic homology was actually through K-theory, in the sense that we were looking to prove this theorem. And so we were searching for a cohomology theory that made this a true theorem. And that's how we stumbled onto this invariant. Okay, I apologize for going over, but I think maybe this is all I should say right now. And I'm happy to answer any questions.
Thank you very much. Are there any questions?
You stated this theorem, AG P infinity, which is like the set of a billion varieties or whatever with some trivialization. So in particular, if you were to look at like just like elliptic curves or something, or curves, right? Then is this saying that the moduli space of curves is a perfectoid space?
The moduli space of curves equipped with such a trivialization is a perfectoid space.
Like a level structure or something like that.
Right, it's infinite level structure at P.
Okay, very interesting. Yeah, thank you.
Right, so it's surprisingly, the theorem is even new there. So it's a new statement about modular curves, which maybe is slightly surprising. Like you wouldn't expect to prove more about them at this point.
Other questions?
So a similar question. How do you say this is a perfectoid space, roughly speaking?
Well, it's hard. I mean, that's like the meat of a 100-page paper. I mean, the rough strategy is that there's something called the ordinary locus, and over the ordinary locus, things are relatively under control. And then what Schulze does is that he first extends the statement from the ordinary locus to a small neighborhood. So there's some precise radius, like a tube around the ordinary locus, over which the same argument that works over the ordinary locus also works. And then he observes that there's I think this is somewhat slightly surprising, which is that there is a group action one can use to move things around. So there is a symplectic group that acts on the whole picture, and it allows you to move everything into the small neighborhood of the ordinary locus to prove perfectoidness.
Thanks.
Bhargav, I also have a sort of down by analogy kind of question again. So, I mean, is there a sort of analog in complex geometry of what a perfectoid space is? So that, for example, if I have some geometric situation where the complex numbers and I know some space is nice, then I would expect some corresponding thing in this mixed characteristic business to be perfectoid. You know, like here, the Siegel upper half space in this space, or.
Right. I don't know if there's a nice class of spaces like that, but like, for example, my intuition has been that Stein manifolds are kind of like this. Like if you have a natural map from a Stein manifold to, like if you have a covering space, for example, of a compact complex manifold by a Stein manifold, then, and if this covering space is sort of defined using like a discrete group, like for example, it's the universal cover and the group is abelian, then you might be able to contemplate a p-adic analog of that. So instead of using the discrete group, you use the corresponding p-adic version. And that should give you a perfectoid space, is my rough intuition. And that's what happens in the elliptic curve example, and also somehow in this AG example. But I don't know any precise theorems like this. It's kind of a heuristic.
Are there some analogs then of this? I mean, there's this conjecture about covering spaces of projective manifolds, right? Are there some analogs in the p-adic setting?
Sorry, what's the conjecture?
That the covering, I mean, if the covering space is not a Stein manifold, then it just has a proper map to a Stein manifold.
I don't know such conjectures, because I didn't know about that one.
That's this famous Shafarevich conjecture that Janos was looking at.
Yeah, sorry, I'm not sure right now of an analog of that.
Okay, so anyway, it's not related to your talk.
No.
Can I also ask a question?
Oh, go ahead.
I know some people are thinking about this theory of motives, and that theory should govern all the cohomology theories supposedly. Like, do you know any like realization function from the theory of motives to your prismatic homology theory?
Well, my impression is that there's a formal way to answer the question, which is like there's a definition of the category of motives. Like if you use Wojewodsky's definition of the derived category of mixed motives, if you want to get a realization, well, sorry, let me take it back. If I use just Grothendieck's definition of Chow motives, if I want to get a realization out of that, I need to be able to construct cycloclasses attached to submanifolds. And if that statement is correct, then the answer is yes, because we know how to define Chern classes of vector bundles and even perfect complexes in this prismatic theory. But I don't think I have like an interesting answer to the question other than saying we can define cycloclasses.
Okay, thank you.
Well, let me thank Bhargav for a beautiful talk. The second talk is tomorrow at the same time, I believe. And then
Can I ask a question?
Yeah.
No, does prismatic homology have Steenrod operations?
I would guess so. I mean, it's given by an E infinity ring, so it should have whatever operations exist on the homotopy of an E infinity ring.
Okay, so then the answer is yes. Then.
Mm-hmm.
Okay, thank you.